In this video, we are going to talk about dimension of a vector space, and here we have our overview slide, which we will spend 1 or 2 minutes going over before we go over each topic in more detail and with more examples. We have this theorem here which defines what a dimension of a vector space is, but before we do that, we have this theorem here which helps us in the proof of our second theorem. So this theorem is if a vector space V has a basis beta with vectors b1, b2 up to bn, then any set in V containing more than n vectors must be linearly dependent. Then our theorem here, which basically tells us that the number of vectors in a basis is an intrinsic property. So if a vector space V has a basis beta, which has n vectors, then every basis of V must contain exactly n vectors. From there, we can define dimension. If a vector space V is spanned by a finite set, then V is said to be finite dimensional. And the dimension of V, which we notate DIMV, is the number of vectors in a basis for V. So dimension of V is the number of vectors in a basis for V. The dimension of the zero vector space is defined to be 0, and if V is not spanned by a finite space set, then V is said to be infinitely dimensional. We have this example here, the standard polynomial basis, 1t and t squared, shows that the dimension of polynomials of degree 2 or less, that's p2, is equal to 3 because there are three vectors in its basis. And in general, the dimension of p sub n is equal to n plus 1. Next, we will talk about subspaces of finite dimensional space, and we'll start with saying if H is a subspace of a finite dimensional vector space V, then any linearly independent set in H is either a basis or, since it's linearly independent, can be expanded to be a basis for H. So a linearly independent set is a starting point as a potential basis. Also, H will be finite dimensional if V is finite dimensional, since H is a subset, and dimension of H is less than or equal to dimension of V. We next have this theorem, the basis theorem, which I like to think of as long as you have the right number of the right types of vectors, you have a basis. So let V be a p-dimensional vector space with p greater than or equal to 1, then any linearly independent set of exactly p elements in V is a basis for V. So you don't have to go and prove that it spans if it's the right number, and the right number being the dimension. So the right number of linearly independent sets will be a basis. And then also, any set of exactly p elements that span V is a basis for V. So if it's exactly p elements, again, the right number, and the right number being the dimension, then you don't have to go and check that it's linearly independent. If it spans it, it's automatically a basis. We will talk about the dimensions of the nullity of A, the column space of A, and the row of A. So we define the terms rank and nullity. So the rank of an M by N matrix is the dimension of the column space. The nullity of an M by N matrix A is the dimension of the null space. And then we have this rank theorem, which is very important. The dimension of the column space and plus the dimension of the null space of an M by N matrix satisfies the equation rank of A plus nullity of A is equal to the number of columns in A. And we have another fact, the rank of an M by N matrix is the number of pivot columns, and the nullity of A is the number of free variables. Since the dimension of the row space is the number of pivot rows, dimension of the row space equals rank of A. Then last, because of all these other theorems, we will have additions to the invertible matrix theorem. So the following are equivalent to the statement A is an invertible matrix. 1, the columns of A form a basis for Rn, and this is assuming A is M by N. The column space of A, the call of A, the column space of A is equal to Rn, and the rank of A, where's the rank? And the rank is the dimension of the column space is equal to n. The nullity of A is equal to 0, and that's the dimension of A, and the null of A is the single element 0, the 0 vector. which means now we have the invertible matrix theorem. We had A through, I believe, L before, and now we're going to add these last 5 statements as being equivalent. Now that we've completed our overview, we're going to go back and take a closer look at dimension. We will have this theorem here, which will then allow us to define dimension. So let's look at those 2 theorems. The first statement we are going to do without proof. If a vector space V has a basis with n vectors, b1, b2 up to bn, then any set in V containing more than n vectors, more vectors than what's contained in the basis, then that set must be linearly dependent. We are going to use this theorem now to prove this theorem here. If a vector space V has a basis with n vectors, then every basis of V must contain exactly n vectors. To prove this, we're going to assume that there are 2 bases. So we're going to have our first basis, which we'll designate as B1. It's a basis of n vectors. And then we're going to say we have a second basis, B2, and it's some other basis of V. And what we want to show is B2 must also have n vectors. Now I'm going to use this theorem up here. I'm going to say B1 is a basis now for V. I'm going to say B2 is my second basis, but it's a set that this statement here says that if this is a second set containing more than n vectors, it must be linearly dependent. But we know since B2 is a basis, it has to be independent, which means it cannot contain more than n vectors. So B2 has no more than n vectors. Again, by this statement, since B1 is a basis, then if another set in V contains more than n vectors, it must be linearly dependent, but since it's independent, it means it must have less than n vectors. Next, we have since B2 is a basis and therefore must span B1, which is linearly independent because B1 is also a basis, then B2 has at least n vectors. And these 2 statements together, that B2 has no more than n vectors and B2 has at least n vectors, must mean that B2 has exactly n vectors. And now we can define dimension. So if a vector space V is spanned by a finite set, then V is said to be finite dimensional. And the dimension of V, which we notate DIMV, is the number of vectors in a basis for V. And the dimension of the 0 vector space, that looks like these brackets, 0 vector bracket, is defined to be 0. If V is not spanned by a finite set, then V is said to be infinite dimensional. A couple of quick examples is the standard basis for Rn contains n vectors, so the dimension of Rn is equal to n, which is kind of intuitively what you would think. The dimension of R3 is equal to 3. It's 3-dimensional. The standard polynomial basis 1t and t squared shows then that the dimension of P2, that is polynomials of degree 2 or less, is equal to 3. In general, the dimension of P sub n is equal to n plus 1, and the space of all polynomials is infinite dimensional. Another example, let H be the span of the 2 3-dimensional vectors 3, 6, 2 and -1, 0, 1. Then a basis for H, well, by definition, these 2 vectors span H, and they are also linearly independent, and you can see that because they're 2 vectors and they are not scalar multiples of each other. To get from 3 to -1, you'd have to divide by -1/3, and that scalar does not work for 6 or 2. So it's not a scalar multiple. These 2 are linearly independent, and they span, and therefore, these 2 vectors are a basis for H, which means that the dimension of H is equal to 2. If we look at this geometrically, now we're in 3 space, we're in R3, we have 2 vectors now in R3, V1 and V2. When we take all the linear combinations, and I believe we discussed this in a previous video, I'm sure we did, that all the linear combinations then define a plane. So H defines a plane in R3. Our next example is to find the dimension of the subspace of H, where H is a subspace of R4. We're in 4-dimensional space now, and our first coordinate is equal to A minus 3B plus 6C. Our second coordinate is 5a plus 4d. Our third coordinate is b minus 2c minus d. And our last coordinate is 5d. And in order to find the dimension, we want a basis. And for a basis, we need our basis to both span H and also be linearly independent. So these are the two things we're going to consider. So we'll start with the span of H. I can rewrite my definition of H, which is equal to a minus 3b plus 6c. And I'm just going to add the 0d, just so everything lines up. Then I have my 5a. I'm going to write 0b plus 0c plus 4d. Then I have 0a plus b minus 2c minus d, and then 0a, 0b, 0c plus 5d. This should be a d here. It sort of looks like an a all of a sudden to me, but it's a d. So now this is what my subspace H looks like. I can break this up then into a times b times c times d. This should be a d. I don't know why it's not there. And then I'll have my a times the multiples here, or the scalars, so 1, 5, 0, 0. I have my b times my negative 3, 0, 1, 0 here. I have my c times my 6, 0, negative 2, 0, and my d times 0, 4, negative 1, 5. So these four vectors here then span my space, because every vector of this form is a linear combination, some linear combination of these four vectors. So these four vectors span H. The question now becomes, are these four vectors linearly independent? It's easy to see pairwise that the 6, 0, negative 2, 0 is equal to minus 2, 3, 0, 1, 0. Now that I pointed it out to you, you may not have seen it right away, but it's the easiest thing to do is sort of get rid of anything that's a scalar multiple of each other. So we know that the four vectors are not linearly independent, but let's say we throw this vector out, v2 out. Are the remaining three vectors linearly independent? And again, if you didn't happen to see this one, I would really recommend you just look at it pairwise to throw things out. But if you didn't see it, it's okay. You can do the same thing I'm about to do for the three remaining vectors. You can do the same thing for the four vectors. It's just a little more work. So between these two, actually I'm going to throw this one out because it has bigger numbers. So I'm going to check v1, v2, and v4. And I'm going to ask, are these linearly independent? So I'm going to see if the homogeneous equation has solution, which means I'm going to take the vector 1, 5, 0, 0, v1, my vector v2, which is negative 3, 0, 1, 0, and my vector 0, 4, negative 1, 5, and set the linear combination of these vectors equal to 0. So I'm going to be row reducing this matrix until I eventually get that x1, x2, and x3 must all be equal to 0, which means the three vectors are linearly independent, which means these three vectors is a basis, and the dimension of H is equal to 3. So subspaces of Rn can be classified by dimension. The zero-dimensional subspace contains only the point 0, 0, 0, this one point. The one-dimensional subspace is any subspace spanned by a single non-zero vector. So if you have a vector, then you can multiply it by a scalar, so essentially you'll get a line. So these subspaces are lines through the origin, because you can always multiply by 0 and you get the origin. Two-dimensional subspaces. Now remember, two vectors will define a plane, so any subspace spanned by two linearly independent vectors are planes through the origin. Again, the origin because you can multiply each vector by 0, and so it's in the span. Three-dimensional subspace is on 3 itself. So any three linear vectors in R3 span all of R3, right? So, and in fact, the I, J, K vectors, or the unit vector in the x direction, in the y direction, and the z direction, you can see that they are a basis for R3 and they span R3. Next, we'll talk about subspaces of a finite dimensional space. And first, we'll start with this theorem. Let H be a subset of a finite dimensional vector space V. So any linearly independent set in H can be expanded if necessary to be a basis for H. Also, H is finite dimensional, and the dimension of H is less than or equal to the dimension of V. I have this theorem rewritten here. H is a subspace of some vector space V. Then any linearly independent set in H can be expanded to be a basis for H. Before we do a proof of this statement, I just want to talk about what this theorem means. It says that we can start with a linearly independent set and then basically expand it until it spans our space and becomes a basis. We're going to look at this theorem together with this theorem, the spanning set theorem, which we had talked about in our video about bases, a previous video. So before I make this comment, let's just review the spanning set theorem. We said if we had a set of vectors, v1, v2 up to vp, and it's a set in a vector space, and we let H equal to the span of our P vectors. So if one of the vectors in A, S, let's just say it's C sub k, is a linear combination of the remaining vectors in H, then the set formed from S by removing our kth element still spans H. And second, if H is not equal to the zero space, then some subset of S is a basis for H. So the idea of this now, if we're looking for a basis of H, and we know we have a set of vectors then that span, we then determine whether or not these vectors are linearly independent. And if they're not, if we find one that's a linear combination is dependent on the others, we can throw it out. So we think about this theorem here, the spanning set theorem, as reducing a spanning set until it is linearly independent and then becomes a basis. So these two are different ways of coming at a basis. Either you can start with a linearly independent set and then keep adding things that are still linearly independent until you have a set that spans and you get a basis. Or the second way of producing a basis is to start with a spanning set and then reduce it till it's linearly independent and then it becomes a basis. So two ways of producing a basis. The first way, starting with a linearly independent set. The second way, starting with a spanning set. The next thing we want to do is to prove that theorem we've been looking at. We'll start if H is the zero vector space, then the dimension of H by definition is equal to 0, which is less than or equal to the dimension of V. So skipping this degenerate case, let's let H not be the zero vector space, then let S be k vectors and they're linearly independent. So this is this set here, a linearly independent set in H. And what we want to do with the set is expand it until we have a basis. So we start, if S spans H, then S is a basis for H, and we're done. If S does not span H, then there's some U sub k plus 1 in H, and U sub k plus 1 is not in the span of S, right? Because we said that S does not span, right? S does not span. So since U sub k is not in the span of S, then U1, U2 up to UK plus this extra vector now is linearly independent by definition of and definition of linearly independent. Then as long as the new set over here does not span H, we keep expanding S to a larger linearly independent set in H. But we know the number of vectors in the set will not exceed dimension of V because we have this theorem here. If a vector space V has a basis with n vectors, then any set in V containing more than n vectors must be linearly dependent. And we know at worst, we're just going to end up using all the vectors in H. So eventually, we have to be able to span. And again, eventually the expanding set will span H. And we'll also see that the dimension of H will be less than the dimension of V. The next we'll have the basis theorem that says let V be a p-dimensional vector space with p greater than or equal to 1. Any linearly independent set of exactly p elements in V is a basis for V. And any set of exactly p elements that span V is a basis for V. I have the basis theorem here, which essentially, in my mind, says if you have the right number of independent vectors, and the right number means the dimension of the vector space, then it's going to be a basis. Similarly, if you have the right number of vectors that span V, and the right number is the dimension of the vector space, then you're going to have a basis for V. And it kind of comes from these two theorems here. You know, you can expand a linearly independent set until it spans the space. Well, you expand this linearly independent set, except that it already has p elements, and the dimension of a vector space is set at p, so you're not going to expand it anymore. You're done, and you'll have a basis. Similarly, here you could think of reducing a spanning set until it's linearly independent. So if you have a spanning set with p elements, well, you're not going to be able to reduce it anymore to get a basis because every basis has p vectors, so, which you have here. So you can't reduce it anymore. I have what I just said written out in proof form. So first, any linearly independent set of exactly p elements in V is a basis for V. And it's because we have, as I said, the theorem, let H be a subset of finite dimensional vector space. Any linearly independent set in H can be expanded and necessary to be a basis. But here, it can be expanded, but the basis must contain exactly p elements, because the dimension of V is equal to p, so you're not going to expand it anymore. Similarly, if you have a set of exactly p elements that spans V, then you have a basis. And from the spanning theorem, you have, so any spanning set then can be reduced to a basis, but the basis must contain exactly p elements. And since you have p elements that span, you can't reduce it anymore. So you must have the right number of vectors in each case. Next, we'll look at the dimensions of the null space, the column space, and the row space. So I have the definition of rank and nullity. So the rank of an M by N matrix is the dimension of the column space, and the nullity of A is the dimension of the null space. So let's kind of review column space and null space. So the column space of an M by N matrix, denoted with column A, is a set of all linear combinations of the columns of A. So if A is the matrix with column vectors A1, A2 up to AN, then the column space of A is the span of the column vectors. And I can rewrite that the column space of A is equal to, by the definition of span, all the linear combinations of the column vectors of A. So to determine if a vector B is in the column space of A, we need to determine if B can be written as a linear combination of the column vectors of A. In other words, we're looking at the matrix equation AX equals B and asking if it has solution for this particular B. And I wrote this here just to get us some of this stuff about what subspaces we're in. So if A is an M by N matrix, in order for matrix multiplication to work, that means X, which is a column vector, so there's a single column. We want to know the rows, so it must have n rows, because remember, when you multiply two matrices, these inner numbers must match, and the result is going to be what's on the outside. So X is going to be an Rn, B is going to be an Rm. So then if B is in the column space, so if A is M by N, then the column space of A is a subset of Rm. It's an m-dimensional space. B is an m-dimensional space. Another way you can think of this is A is M by N, which is m rows and columns. So you have the columns, those are your column vectors, you have n of them. So that means each of these have n coordinates. Each column vector has n coordinates. And so when you add them up, at the end you're going to get a vector with m coordinates. So you can think of this either way. I sort of like looking at this equation here. And to review what the null space, so I should go back. So that's the column space. So the dimension of the column space, that is not, the dimension isn't necessarily Rm. It's because the column space is a subspace of Rm. It could be a single vector. If Rm, let's say, is R3, the column space of A could be a single vector, in which case the dimension is going to be 1. So the dimension, the basis, the number of vectors in the that form a basis for the column space then is called the rank. Next, we should look at the null space so we can talk about nullity. So the null space of an M by N matrix, denoted null of A, is a set of solutions of the homogeneous equation AX equals 0. So in set notation, the null of A is equal to the vectors X such that AX equals 0. So to determine if x is in the null of A, we're going to compute AX and see if the solution is 0. So if A is m by n, and I'm going to look at this picture up here that we looked at for column space. So A is m by n. That means it's going to multiply vectors that are n by 1. These vectors x, these are the vectors that we're checking to see if it's in the null space or not. So it's an n-dimensional vector. It's in Rn. That means the null space of A is a subset of Rn. And then how much of Rn is, or how, the dimension of the null of A then is called the nullity of A. Oh, and it looks like I had drawn that AX kind of diagram down here. So X is going to be n by 1. It's part of Rn. So again, it's important to remember that the column space of A is a subset of Rm, but the dimension of the column space then is the actual, it's not necessarily equal to m, but it is something less than or equal to m. Similarly, the null space is a subspace of Rn, and the dimension of the null space is going to be n or less, less than or equal to n. Before we do an example, we have one more theorem, the rank theorem, which is the dimension of the column space and the null space of an m by n matrix satisfies the equation that the rank of A, that's the dimension of the column space, plus the nullity of A, that's the dimension of the null space, equals the number of columns in A. And we have this proof here, which I'm not going to go through, but I have it here for your reference. And one more statement from here. The rank of an m by n matrix is the number of pivot columns, and the nullity of A is the number of free variables. Since the dimension of the row space is the number of pivot rows, then the dimension of the row space equals rank of A. I think it's a good time for an example. So we want to find the rank and the nullity of A. Again, that's the dimension of the column space and the dimension of the null space. A is the matrix with the column vectors -3, 1, 2, 6, -2, -4, -1, 2, 5, 1, 3, 8, -7, -1, -4. For whatever reason, I decided I wanted to start with the null space. So I looked at the set of linear combinations, the first vector times x1 plus the second vector times x2, etc., equal to, and for the null space, I set that equal to 0. So this is my augmented matrix, my A matrix with the 0, 0, 0. I row reduced, and this is what I found, that x4 and x5 could be free. Then x3 would equal to minus 2x4 plus 2x5. x2 would be free, and then x1 would be equal to 2x2 plus 2x2 plus x4 minus 3x5. So again, the null space are the vectors x that get sent to the 0 vector by our transformation A. So the null space looks like the x's such that, what do we have? x2, x4, and x5 are free. x2, x4, and x5. x1 is equal to 2x2 plus x4 minus 3x5, and x3 is equal to negative 2x4 plus 2x5. So I can separate that out. I have my 3 variables, so there's going to be 3 vectors, and this is the vector that gets multiplied by x2, which is 2, 1, 0, 0, 0. This is the vector that gets multiplied by x4, which is the vector 1, 0, minus 2, 1, 0. And this is the vector that gets multiplied by x5, which is minus 3, 0, 2, 0, 1. So this is our basis for the null space of A, which means the nullity is equal to 3. Now the column space of A is the space spanned by the column vectors of A. So the space spanned by the vectors -3, 1, 2, 6, -2, -4. By the way, this is a linear combination. So 6, -2, 4 is equal to 3, 1, 2 times -2. So if we were looking for a linearly independent set, we could eliminate this one. And then we also have the vector -1, 2, 5, 1, 3, 8, 7, negative 1, 4. So I have these 4 vectors. I need to determine if they're linearly independent. And if they're not, I need to throw one vector out. Then I need to look at my remaining 3 vectors, determine if they're linearly independent. If they're not, I need to throw one out until eventually I have a linearly independent set. Or the other more desirable method of doing this is to use one of these 2 theorems. So first, over here, I used this theorem over here. The rank of an m by n matrix is the number of pivot columns. So here I'm looking at the rank of A is equal to 2 because when you look over here, there is this column with a pivot and this column with a pivot. So the rank of A is equal to 2 because there are 2 pivot columns. Or I could use this theorem here. The rank of A plus the nullity of A equals the number of columns of A. So there's 1, 2, 3, 4, 5 columns of A. The nullity of A is equal to 3. That must mean that the rank of A is equal to 2, which is good because that's the same exact answer I got as using this other fact here. Our next example, if A is a 7 by 9 matrix with nullity equal to 2, what is the rank of A? Second, could a 6 by 9 matrix have nullity equal to 2? The first question, A is a 7 by 9 matrix, nullity is 2, what is the rank of A? So we're going to use this first theorem up here, which says the rank plus nullity equals number of columns. So in other words, we can just subtract nullity from both sides and we get the rank of A is equal to number of columns minus nullity, which I have written here. So the number of columns, 7 by 9, 7 rows, 9 columns. So 9 columns minus the nullity, which is equal to 2, which means the rank must equal to 7. Next question, could a 6 by 9 matrix have nullity equal to 2? We'll start. If it's 6 by 9, that means there's 6 rows, 9 columns. And by our rank theorem here, the rank plus nullity is equal to number of columns, which means our rank is equal to number of columns minus nullity. So the number of columns, this is row, this is columns, so 9 columns minus 2, that's the nullity, is equal to 7. So rank is equal to 7. And remember, rank is the dimension of the column space. So before we say yes, let's look at this. So isn't that suspicious when I say before we say yes? We need to look at this. So A is an m by n matrix. We multiply it times vectors, which need to, because of matrix multiplication, it needs to be n by 1. That means our B vectors then are going to be m by 1. And just to make this clear again, we can think of A as a mapping then from Rn to Rm. In other words, we take vectors x, which are in Rn, and we map them to vectors in Rm, B vectors in Rm. So the thing is that the rank, these are the vectors B that can be written as a linear combination of the column vectors of A. The rank is a subset of Rm. So I'll write that out. Rank then is a subset, in this case, Rm is 6, R6. So the rank then, the dimension of the rank has to be less than or equal to 6. So that means rank equals 7 is not possible. And so that means the nullity of 2 would not be possible. Our next example is we have a matrix A with column vectors 3, 3, 4, 0, 0, 0, negative 1, negative 1, 5. And we want to find the null space, the column space, and the row space. And I think this is good to do, so I'm going to try to do this from now on. So our matrix A is 3 by 3, which means the vectors we're multiplying, the vectors x we're multiplying, are going to be 3 by 1. And it's 1 because it's a vector, it's not a full matrix. And then also our resulting matrix, getting rid of the 2 3's, is going to be 3 by 1. So A is a mapping from R3 to R3. To find the null space, we're going to see the x, the vectors x that get mapped to the 0 vector. So we're going to look at the augmented matrix of A and the 0 vector. That row reduces, and it tells us that x1 must equal to 0, x2 is free, and x3 must equal to 0. So here we have a single vector, 0, 1, 0, that gets multiplied by x2, and that is a basis for the null space of A, meaning the nullity is equal to 1. Now the column space are all the B, the vectors B, that are a linear combination of A. So I have the augmented matrix of A with the vector B, which has coordinates b1, b2, b3. And when I reduce this matrix, I get that b1 is equal to b2. So this is the span of the B1, or this 1, 1 vector covers the B1 equals B2, and then this is the only condition, so B3 is the third vector over here. The third coordinate can be something as well. So that means the 1, 1, 0, 0, 0, 1 is a basis, and rank equals 2, which is good because now we have the number of columns of A, which is equal to 3, is equal to our nullity plus our rank. So that's sort of a little sanity check here that our answers make sense. Now we'll look at the row space, and the row space are the linear, it's like column space, but instead of linear combinations of the columns, it's linear combinations of the rows. So our rows are going to become our new columns. So our first row is 3, 0, negative 1, so that's my first column. My next row is the same as the first, so I don't need to write it again. Then my last row is 4, 0, 5, that's my next column. And I want the vectors B that can be a linear combination of these two columns. So here I have my augmented matrix and my vector B, which has coordinates B1, B2, B3. And when I row reduce, I get the fact that B2 must equal to 0. So B1 can equal to whatever, and B3 can equal to whatever, but B2 needs to be equal to 0. So 1, 0, 0, and 0, 0, 1 is a basis for the row space of A, or row of A. We have here sort of another application-y sort of example. So we have, and this is actually kind of interesting. I thought it was going to be not so impressive, but it's interesting. So a scientist has found 2 solutions to a homogeneous system of 40 equations and 42 variables. So how many rows are there? There's 40 equations, 40 rows, 42 columns. Yes, yes, that's correct. The 2 solutions are not multiples. It's 2 solutions of this matrix A. And all other solutions can be constructed by adding together multiples of these 2 solutions. Can the scientists be certain that an associated non-homogeneous, remember this is for the homogeneous, now the non-homogeneous system with the same coefficient has a solution? I like to start by organizing my information. I have 40 equations. You know, I think of writing equations along a row. So I have 40 rows. That means my 42 variables, I have 42 variables or 42 unknowns. So my matrix is 40 by 20. That's, rows, columns, 40 rows, 42 columns, m rows, 40 rows, and 42 columns. I write it this way too. AX equals B, so A is 40 by 42. That means X must be 42 by 1 because these dimensions have to agree. So you sort of cancel them out and you get the dimensions of B, 40 by 1. So A is a mapping from R42, right? X is in 42 dimensions, and B is in 40 dimensions. So my next statement is I have 2 solutions that are not multiples. And remember, there are 2 solutions to the homogeneous equation. So let me just underline that. 2 solutions to the homogeneous equation. They're not multiples of each other. So what that means are 2 solutions. And here I have x1 and x2. These are vectors, by the way. Sometimes, when we talk about the vector x, then x1 is the first coordinate. But I put this arrow to suggest x1 is a vector, x2 is a vector. So these are my 2 solutions. They're not multiples of each other. In other words, they're independent. And then we also have this fact that all other solutions can be constructed by adding together multiples of these 2 solutions. In other words, all solutions to this homogeneous equation are spanned by the 2 vectors, 2 independent vectors, meaning these 2 vectors then form a basis for the homogeneous equation, meaning the nullity of A is equal to 2. So that's what I get from these sentences here. So finally the question, can the scientist be certain that an associated non-homogeneous system, so now we have AX equals B for our non-homogeneous system, can they be certain that there's a solution? Well, what we have now is the rank. So we're looking at the dimension of the rank, just because, I don't know, that's where we are in this chapter, I guess. And the rank is going to be equal to the number of columns minus the nullity of A. So the number of columns is 42. The nullity of A is equal to 2. So that means the rank is equal to 40. So 40 is the dimension of the column space of A. And then looking at this, since A goes from R42 to 40, that means the rank of A is equal to 40. So the column space of A spans all of R40. And for every vector in R40, AX equals B has a solution. So yes, every non-homogeneous equation with same coefficient matrix A will have a solution. So this is actually quite an interesting example. I'm always a little suspicious when people try to make this application example, but this one actually is a good one, so make sure you take a look and understand it. Now that we've gotten through the rank and the nullity and the rank theorem, we have additions to the invertible matrix theorem. Some of these I think came from the previous video, and then no, actually these are all from this video. Okay, never mind. So we have additions to the invertible matrix theorem based on what we've talked about in this video. So the following are equivalent to the statement A is an invertible matrix. The columns of A form a basis for Rn, the column space of A is equal to Rn, the rank of A is equal to n, the nullity of A is equal to 0, and the null of A is the 0 vector. And so this would now be our augmented invertible matrix theorem. At this point, we've gone over all the material for this video, but I do have a few more examples for you. But since we've gone over all the material, I suggest that after this problem statement for each problem, you pause the video and give the problem a try before you look at the solution. The first problem is a true or false problem with two parts, and we're given V is a non-zero finite dimensional vector space. So part A, true or false, if dimension of V is equal to P, and S is a linearly dependent subset of V, then S contains more than P vectors. Part B, true or false, if S spans V and T is a subset of V that contains more vectors than S, then T is linearly dependent. So this statement is false, and I'm going to show that with counterexamples. First, let's assume that the dimension is greater than or equal to 2. So then, for example, you can choose any vector from V. Let's call that V1. This is our vector. And we're going to construct a set S that's linearly dependent and contains more than P vectors. So to be linearly dependent, we need at least one more vector. So let's just choose 2V. And we know 2V is part of the vector space V because vector spaces are closed under scalar multiplication. So now we have S. We've constructed a set S that's linearly dependent. It's a subset of V. And then you can see that it contains two vectors, which is not more than dimension greater than or equal to 2. So it'll be dependent and does not need more than two vectors. But what happens if dimension is greater than or equal to 1? We can choose S to be the zero vector space, and by definition it's a subset, it's linearly dependent, and it has dimension. We only need one vector. Actually, this will work for any dimension, but I feel like this is a better illustration. Part B, true or false, if S spans V and T is a subset of V that contains more vectors than S, then T is linearly independent. I started by writing a basis for V, and I assumed that V has dimension n. Looking at this part of the statement, if S spans V, so if S spans V, then S has at least n vectors, because a basis is a minimum spanning set. Next, we're going to look at this part of the statement, T is a subset of V. So if T is a subset of V, it is entirely contained in V. So if T is a subset of V, a basis for T can't be any bigger than a basis for V. So that means a basis for T must have at most n vectors. Next, we'll look at this part of the statement. T contains more vectors than S, but we have here that S contains at least n vectors. So n vectors or more, and if T contains more, that means T contains more than n vectors. So we know the basis must have at most n vectors, but T contains more than n vectors. So I wrote that statement here. The basis contains at most n vectors, so less than or equal to n vectors, whereas T itself contains more than n vectors. But since the basis is the largest independent set, T must be dependent. So that's true. T is dependent. There are two views of the basis that we learned about in the last video about bases, which we used here. First is that the basis is a minimum spanning set, and second, the basis is the largest independent set. Our next problem, let H and K be subspaces of a vector space V, then the intersection of H and K is also a subspace of V. Then prove the dimension of H intersect K is less than or equal to the dimension of H. And I don't know why, but I went ahead and proved that H intersect K is a subspace, but since it wasn't part of the problem, I'm going to leave this for you as for your reference, but I won't go through it. But I will look at the problem. Dimension of H intersect K is less than or equal to the dimension of H. So I'm going to start by providing a basis for H intersect K, and I'm going to assume that H intersect K, the dimension of H intersect K, is equal to P. So the next statement I will make is H intersect K is a subset of H, right? Because, well, it is. So B is linearly independent because it's a basis, but it may not span H. So now B can be our starting set for a basis, but we'll need to add more vectors until we get the span of H. So we can expand B with the beta with additional linearly independent vectors to make a basis. So therefore the dimension of H must be greater than or equal to P because we're going to be expanding it, which is equal to the dimension of H intersect K. I have a second way of looking at this, but I really like this way more, but I'll leave this here for your reference. So to review the things we covered, we talked about the dimension of a vector space, and we started with this theorem here to help us prove the theorem we needed to get to the definition of dimension. So we said if a vector space V has a basis with n vectors, then any set in V containing more than n vectors must be linearly independent. That helped us prove the fact that if a vector space V has a basis with n vectors, then every basis of V must contain exactly n vectors. In other words, the number of vectors in a basis is an intrinsic property. It doesn't change. So from there we can define dimensions. Since the number of vectors in a basis is intrinsic, we can say the dimension of a vector space V is spanned, if it's spanned by a finite set, then V is said to be finite dimensional, and the dimension of V, notated DIMV, is the number of vectors in a basis for V. The dimension of the zero vector space containing only the point 0, 0, 0 is defined to be 0, and if V is not spanned by a finite set, then V is said to be infinitely dimensional. And we had this example. Our standard polynomial basis, 1t and t squared, for polynomials of degree 2 or less, shows the dimension of the space P2, which is polynomials of degree 2 or less, is equal to 3 because we need 3 vectors to cover it. And in general, dimension of polynomials of degree n or less is equal to n plus 1. Next, we talked about subspaces of finite dimensional space. We said let H be a subspace of a finite dimensional vector space. Any linearly independent set in H can be expanded if necessary to be a basis for H. And we also said H, if it's finite dimensional, H will also be finite dimensional if V is finite dimensional, and dimension of H is less than or equal to dimension of V. Then we had this basis theorem that said let V be a p-dimensional vector space with p greater than or equal to 1. Any linearly independent set of exactly p elements of V is a basis for V. And any set of exactly p elements that spans V is also a basis for V. So this makes finding bases much easier than proving spanning and linearly independent. Next, we talked about dimensions of the null space of A, the column space of A, and the row space of A. If you recall, the null space of A are the vectors x that get mapped to the 0 vector. The column space of A are all the linear combinations of the column vectors of A. The row of A is all the linear combinations of the rows of A. So then from there we defined rank and nullity. The rank of an m by n matrix is the dimension of the column space. The nullity of A is the dimension of the null space. And then we had the rank theorem, which is very important. The dimension of the column space in the null space of an m by n matrix satisfies the equation rank A plus nullity of A is equal to the number of columns of A. This next fact here, if you can manage to remember, it can come in handy. The rank of an m by n matrix is the number of pivot columns, and the nullity of A is the number of free variables. Since the dimension of the row space, and this is just kind of bonus, this is probably more important to remember, but since the dimension of the row space is the number of pivot rows, the dimension of the row space is equal to the rank of A. Last, because of these different theorems here, we have additions to the invertible matrix theory, which now looks like the same invertible matrix theory that we had, but we had the addition of the column vectors of A form a basis for Rn, the column space of A is equal to Rn, the rank of A is equal to n, the nullity of A is equal to 0, and the null of A is the 0 vector. So that's it for this video. Thank you for watching.